All right, well, I think we should probably go ahead and get started here. This is a webinar put on by Quantum Computing Inc. To describe how to use our Mukai platform. I am Steve Reinhardt. I'm a VP of Product Development. I will just be briefly introducing things here, and most of the time will be used by Jesse Burwald, talking about getting started with our Mukai platform. You'll also hear at various points, possibly Uchenna Chukwu and Raouf Dridi answering questions. Feel free to put questions in the Q&A at any time. Some of those will probably surface to Jesse in real time. Some of those we will probably keep until later, and some we will, the rest of us will answer in real time. So whatever works there is great. So with that, I'm gonna maybe just preface Jesse's main part of the talk with a couple slides here. What are we doing? Who is quantum computing? Why should you care, et cetera? So a little bit about our mission and technical strategy. So our mission is to deliver superior performance now from quantum-ready applications and tools. So this, we feel like we need to appeal purely classically at the outset because we want to get adoption of quantum-ready methods, and not clear when that's going to have quantum advantage. So we need to give some type of advantage now. We want to accelerate the routine use of quantum computers when they do deliver advantage. And we want to, by working on this now, we want to broaden the range of applications that are able to take advantage of quantum computers when they do deliver advantage. And our Mukai middleware is available in the cloud today, delivering superior performance. Oh, I jumped ahead here. I forgot to, when we say quantum ready, this is a term that we're all used to because we use it all the time, but let me step back and define that. So what we mean is by quantum ready is it's developed using methods that map directly to quantum computers. So if you're writing an application and use a quantum ready method, there's no change for you later when we shift from running purely classically today to running in a hybrid classical quantum mode in the future, which pretty much everyone believes will be the way that we'll first get advantage from quantum computers. So quantum ready applications and tools, performance now. A little bit about our technical strategy at QCI. The arrival date of quantum advantage is uncertain. It could be with the D-Wave Pegasus system in another year or two. It could be with gate model processors that are not error corrected in maybe 3 or 4 years. And it could be error corrected gate model processors, which are 10 or 12 years away. So that uncertainty is a big deal. We need to insulate application developers and users from that uncertainty. So that's one of the first things we do. We also want to insulate application developers from machine-specific details, the number of qubits, the topology, the specific supported gates, et cetera. Number 3, as I said earlier, we want to deliver superior performance now. This is not quantum performance, so it's not 1,000 or 1,000,000 times faster, but we feel like to be successful in the marketplace, we'd have to deliver some performance benefit now. And last, we at QCI are focusing on constrained optimization. So, you know, this will come up again in the course of discussion, but there's things like the best delivery route, the best schedule for aircraft engine repairs, the best folding of a protein, et cetera. Constrained optimization is not everything that quantum computers can do. But we feel like it's important to focus on something, get very good at it, because doing these first 3, even for the a specific area like constrained optimization, is a lot of work. So we want to get that right before we defocus ourselves a bit. Now I will turn it over to Jesse and to walk us through getting started with Mukai. So I will stop sharing. And Jesse, you should be able to share.
Steve, yeah, let me here. Should be. I'm lost in my screens.
Jesse, I am just barely hearing you.
Okay, yeah, no, I'm trying to actually when you stop sharing screens, there we go. Let me do one thing. It moved some of my screens around. I will. Yes.
Okay.
One moment here. Let's see it.
A little head fake.
Yes. And that should do it. Can you guys see that? Is that?
Yes.
Okay. All right. Good. The little green bars didn't go around it, so it's unclear. Anyway, so yeah, this is my presentation for I want to give an outline for how to get on to.
Hey Jesse, you want to maybe use your camera?
Sure.
That's off.
Yeah. Was it off? Oh yeah. Actually, yeah. Earlier it was. I can. Hide on video. Hold on. Oh, I'm muted. And now I'm unmuted again. I'm unable to start video. I think it's a host issue.
Oh, okay.
Yeah, sorry about that.
Yeah, no problem. Charge ahead.
But if you turn it back on, it's fine.
Okay, I will try to do that.
Yeah, earlier I had tried, but
okay,
no worries. Let me try. Okay, so yeah, let me start again here. So we want to actually just start it. We're going to start at a pretty high level here and walk people through how to install Mukai and a couple slight technical issues with just, it's a cloud system, how to actually set up the access token just to make sure this is a one-time deal. And so I guess one brief thing is it's not actually explicit here, though if you read through this briefly, you'll see it. Mukai is a Python-based system, at least on the front end. It's all just a Python web API. Uses the traditional requests package, all that sort of stuff. There's various other core systems on the back end, but if you're familiar with Python and you can Google around if you're not, it's pretty easy to get going. I'm not going to deal with setting up the actual Python system. I will deal with setting up, as I will assume that people have their sort of favorite Python system up and running. So first, we'll sort of deal with, here's the outline. We're going to install and configure Mukai. We will just explore two systems. There's basically broken into two systems, sort of a constrained optimization system, and then a module that deals with essentially graphs. And so that'd be graph analysis, like partition. We'll deal with partitioning and a small example on community detection. So let's go through sort of the drier technical part first. First, if you're gonna run this at home, we're gonna post this the notebook up right after this webinar. So if you run it at home, I just sort of did a basic thing. You can do it however you want, but I make a directory in my little sandbox, Mukai webinar I called it, and I CD into there. And these Jupyter notebooks are great. So I've got a terminal here, and I'm actually in the my little Mukai webinar folder. And we want to actually install. So I'm going to do a little properly here. We're going to actually create a virtual environment. So if you're not familiar with that, it's probably a good habit to get into, especially if you're testing new stuff. And I'll just create it in a little hidden folder. That creates a Python 3 virtual environment. As another tidbit, worth mentioning, though, I think it's far enough along that everyone has switched to Python 3, but Mukai is purely Python 3. So if you're still on Python 2, yeah, it's time to switch. So we need to activate this. We'll just activate it. And so now we're in the Mukai, sort of our Mukai environment, and we want to just install. So we're going to install Mukai just from pip, and it's got a few dependencies, normal numeric libraries and stuff like that. The request package, pandas for tabular data and stuff like that. And it's downloading it all, and once it's installed, okay. So that's basically the install step. Typical Python install, nothing too big. Now it's a cloud system, and so we have to, every time you run a problem, you're going to have to actually authenticate to to the server. So instead of doing that every time, and if anyone runs anything in production at a company, basically you need a file of some sort that holds your credentials. And so we're going to create a little credential file. I have mine over in basically my home directory, .qci.conf. And let me paste this up here. This is all written down here in the documentation too, so you can see this. So when you start a trial license or a regular license, you end up, we send you an access token, and it looks something like this. It's actually much longer. And what it says is I want to use my default environment will be defined by default, and the client will grab the access token, and there's a default sampler, which we call QB solve, which is a heuristic sampler that we'll be using in the back end. Yeah, so we could go through that, but let me just show you real quick how we would, what it should look like. So I'm just going to copy this down here, and from probably the documentation page, you could copy that and paste that, or from an email we'd send you, and just make a little file here. QCI make it hidden this time, and just paste it in. And you want to get the tabs right, unfortunately. It's a two-space system for YAML files. And then right here, just paste in whatever your access token is. So I'm going to just write my access token. And you'd want to copy that on a Mac or Linux system, copy that to the user directory. And for Windows, it's slightly different, but it's basically in the user, your sort of the C drive and the user directory, which is more or less equivalent to saying the following: cp QCI comp to home, like the home directory. And so that's really all you do, and that would set you up for the rest of the time. So you don't have to enter your password or your access token or anything like that. So that's all set up. And let's see. So assuming that's all set up and there are no problems, you can continue on. So what we want to talk about now are the three main things that we can do. Two of them are kind of in the same category, and one is slightly different. They're all constrained optimization, but they kind of look a little bit different. So first is just, we're going to look at some raw constrained optimization problems. Sometimes you end up having constrained optimization that is sort of baked into a QUBO, a quadratic unconstrained binary optimization problem. And so we can deal with that too. There's a little less flexibility there, and you'll see why as we go through this. And then there are graph problems, which on the back end can be converted to constrained optimization, but you can send in a network X graph, which is a nice convenience, I'd say. There are many network problems out there that, like a traveling salesman problem or something, can be essentially formulated as a graph and then converted over to a constrained optimization problem. Okay, so As with anything numeric in Python, we're going to start by importing NumPy. And we're going to also start by importing our Choir package. So Choir is basically constrained optimization, and the IR is sort of an intermediate representation. So intermediate representation is sort of the technical computer term for, we want to turn like a graph into an intermediate representation that we can actually manipulate and make more efficient on the back end. So that's Choir is sort of an intermediate representation for quadratic optimization work. Q, because it's quantum, so they had, that's how it has to be. But so we import NumPy, we import Choir, and we have a little tiny optimization problem here. This is a basic objective, also known as cost function. And so if we step back up here, the basic constrained optimization problem is we want to minimize some f, which is our cost function down here, subject to some constraints. And in their case, these are sometimes called combinatorial optimization problems, but we are dealing with binary variables. So we want to optimize this cost function, find a minimum or sometimes maximum value of f with binary variables and subject to these constraints. So another way to say that is, these are actually A is actually a system of linear equations, and Q is some square matrix with that acts as a cost function. So what's up here is equivalent to what's down here. You can see we can do a couple things with this. First, there's sort of a default. I called this out here, but you don't have to actually. The default is setting alpha equal to 1. You have to combine these in a certain way to get a QUBO out of them, which is how we're going to deal with this on the back end. But you have a lot of flexibility if you come in and you have these separate. So let me run this real quick. And what we're asking for is essentially, find the minimum value, the minimum energy it's called often, or cost, or if you're doing a traveling salesman, it would be distance, whatever your metric of that you're trying to minimize or maximize is. So, and we're going to subject it to these constraints. And what we're going to do is essentially just upload the matrices, do the math that's necessary to combine them on the back end with a Lagrange multiplier of 1 between them. Okay, so what comes back is just, there's a few solutions that come back. It's a small problem. There aren't too many. And we want to actually see, it's interesting that because this is combined into a QUBO, it's the quadratic unconstrained. The constraints are baked in. And so we have to go back and quickly check and see, did everything actually satisfy constraints? So we found some things, some answers with low energy, but they may not have satisfied our constraints. So we can go and take the response and ask, okay, so given our constraints, our constraint matrix, were things satisfied? And in this case, the answer is no, not for all of them. And so we see that actually only like the last one here was actually satisfied constraints. And that's fine. I mean, that gives us actually, in this case, probably not the best solution we could find. It looks like there are other solutions maybe hidden in here. So we're going to actually, what we can do is, because we actually have, scroll up here, we have this system of linear constraints, and it's a system of equalities. We can actually use the Lagrange multiplier method. And so that's, there are many versions of this that we've seen from calculus and in various realms, but essentially for all intents and purposes, or our goal here, we can modify the importance of the constraints in the overall problem by modifying alpha, which is essentially a multiplier that we can stick in front of the A matrix. And what we're going to do here is actually just modify it a little bit. So we basically multiply it by 5, so it's 5 times more important. Okay. So what we see here is actually, just to briefly call this out, we actually have, it doesn't matter here, these are such small problems, but there is an upload progress. So, it gives you a little upload bar. So if you have, a 5,000 by 5,000 matrix or something, or for your cost function, it'll take 30 seconds to upload or something. So you can, gives you at least a notion of how things are progressing. We got more solutions, and we actually found more. You can, the multiplier changes the energy, but we found more. We actually found 5 instead of 4 solutions, and we can see how many actually satisfied constraints. We found 1 more satisfied constraints. So we're sort of, by increasing the importance of constraints, we can actually come out with more feasible solutions. So that's a helpful, essentially a helpful way of, if you have a constraint optimization problem, you can iterate over various values of alpha. Now, you may not want to do that, and if you're like me, or you've done any sort of machine learning or optimization problems, you end up tweaking parameters all over the place. Whenever you can optimize this situation, you end up doing that. So instead of actually, this is a nice convenience function. We're basically sampling the constraint problem. Very straightforward. We have a cost and a constraint matrix, and we can modify how they are combined with the alpha. But we don't necessarily have to do that. We could actually sample the Lagrange optimization, which is saying we want to sample from the solution space, and we want to optimize the Lagrange multiplier. And so you'll note there's no actual alpha here. So we can actually send in the cost and constraint matrices. And actually, based on when, let me think. Basically, when constraints are not satisfied, we can actually determine that alpha is not adequate. And we can modify alpha as needed until we find the constraints are satisfied. So if we do this, this actually will take a teeny bit longer because it had to actually go and do a couple rounds to figure out the optimal alpha. And so we see actually automatically we found actually the same solutions pretty much. The energies are a little tough to interpret. You can actually find, because Q never changes, you can go back and find the actual cost, which I haven't done in this case, but you can multiply all the feasible solutions by the cost and figure out which is the minimal one. But because we've modified, the energies are calculated with the whole multiplication in here. You end up having sort of slightly different costs. So that's just a little post-processing step that's easy to handle. Yeah, so we found actually the same solutions, you see, but we actually didn't have to work at it. Up here, we may have had to go, I just kind of randomly chose alpha to be on, here as 5, to be honest. If you're going to do a systematic study, you may have to, have a little linear space of alphas from 1 to 10 and figure out which is the minimum one that gives you the best solution. This automates that whole process. And what we actually find is that the alpha it ends up with is a vector of alphas. And so alpha, what it's doing is actually, scroll up here. Because we're multiplying this matrix here, what we can do is actually modify each constraint, each row is a constraint. And so that's why we have a vector that's linked to, is we actually are multiplying each constraint by a certain alpha, alpha 0, say, and alpha 1. And that ends up giving us actually optimal, same feasible optimal solutions. So that's sort of a handy feature. I think I use it all the time actually. So let me think. So that covers very quickly, I think, 2 of the main components that we have. Sort of a hands-on constraint optimization solver and a slightly more automated constraint optimization solver with sample Lagrange optimization here. There is sometimes the case where you have a QUBO, or so it's physicists know these as icing problems, but things are sort of baked in. You don't have that constraint matrix A. The whole thing is one big cost function. It's quadratic unconstrained binary optimization. Sometimes you can form this by actually, basically what we're doing is forming this in the background based on the cost and constraints. But if you don't have that, we have a function where you can actually just sample the QUBO. So we have very tiny QUBO here. I want to point out, it's assumed that QUBO's basically a square symmetric matrix. That's the easiest way to represent it. And we also accept sparse matrices and stuff too. So And oftentimes these are quite sparse, in fact. So it would behoove people to actually consider that if they have a QUBO. Here's sample the QUBO. Same procedure, just upload it, use the same heuristic solver on the back end, and it returns some solutions. This is a nice opportunity to actually show that, if you do a fair amount of data analysis, you can't help but to have noticed that there are data frames out there. And you can do possibly better, easier analysis with the data frame. So there's a quick, easy two pandas method. And so you can do whatever statistics you might want there. So in this case, this is actually a 3x3 matrix. It's 2 to the third. There are actually only 8 possible solutions one will ever come up with. So that's what we're seeing here. And there's another thing to point out with all of these, and this is just sort of the response that we got back is an object, and it contains various things. Like these are actually, the energy is actually an array. So what you see printed out here is counts are arrays and energies are arrays. So I'll just print out the samples. It's actually, a 2-dimensional number array. So another way to do statistics or various things is just to slice that up if you're familiar with that.
Hey, Jesse,
yeah.
Maybe
yeah.
I would interject here that the underneath sample QUBO is the QCI version of QBSolve, the open source QUBO solver that has been actually it's been used by a huge number of early projects targeted at the D-Wave quantum processors. And at QCI, we have dramatically improved the performance in energy value, speed, and diversity. But many people may be familiar with QBSolve as a solver, and it has that same lineage underneath.
Yeah, thank you. Yeah, I was thinking that would probably come up as a question at some point. So.
Oh, yeah.
Good. So yeah, that's what's being used as the heuristic solver on the back end here. And it's also what's being used for graph problems. So as I mentioned, all the graph problems can be converted straight to some form of constrained optimization problem. And let me go through it. So this is actually slightly different, only in the fact that we are actually going to import network X. And this is a different module within Mukai. So we're going to import QCI network X as QNX. You can think of it as a wrapper around a number of graph algorithms. And the wrapper essentially takes the graph and converts that into a representation that's amenable to QBSolve for sampling. And so a simple example, just to show how this works, is we can create a barbell graph, which is pictured down here, and we'll draw it. Pretty straightforward. There are 7 nodes in each weight at the end of the barbell, and there's a 5-node bar between them. And we want to partition this, right? We can do this by hand or by visual inspection, of course. We're going to optimize the node partitioning, though, with QNX partition. All right, so we're going to take this graph. I'm going to send this over to the solver. And what it'll do is actually take, the partition has a particular combinatorial optimization or constrained optimization formulation. And so we're just going to convert the graph into that formulation on the back end and return the samples. And what we see is, hopefully we'll see that, in fact, because it's a heuristic solver, you will always get, for this problem especially, we'll always get these top 2 solutions. And every time I run it, I either get neither of these or 1 or 2 of these. So these are slightly different. These are, I think, basically the solver started a slightly different random spot and found a slightly different cut, which is slightly non-optimal, as you can tell. These cuts here are exactly what you'd think. If you look at this, you can cut essentially between 8 and 9 or 9 and 10. And so let's actually go and check this out. One thing that's interesting is a graph, we have to convert it back, but you can see we don't want to modify the original graph. We want to take the labeling, because essentially we put these two sides of the graph into two components. And we partitioned it, and we essentially labeled them by 0 and by 1. And we don't want to modify the original graph, so we sort of map the 0th solution right here to a new graph. We essentially copied the old one and pushed the labels onto the nodes here. So if you're familiar with network X graphs, essentially we've said that node 0 has a label of 1, and then at the bottom node 18 has a label of 0. So we've done that. And we can plot it. And so, you know, this is sort of intuitively what you'd expect. Essentially node 0, green is represented by 1 in this case, and node 0 is, this is the first partition, the second partition. And we can map the second one. And if you're familiar with partition algorithms, and especially things like this, there's a certain symmetry involved. One would expect that, in fact, the other possible solution, 9 to 10, is essentially symmetric with 8 and 9. They have the same energy. So those are our top two solutions. And these are some other ones. I'm not going to plot them, but essentially, you can see also that, you know, because we sampled a number of times, it's these are essentially anomalous solutions compared to the frequency of the others. You can see it that way too. So you can actually look at these in a probabilistic way too, which is actually handy in a lot of situations. All right, and then we're going to end with the classic, very classic, possibly overused, but actually quite interesting karate club example. So we actually, the question came up in preparing this, what exactly was the karate club? Zachary's karate club. And yeah, it was just it's just a network of relationships, you know, in the university karate club that was published in the Journal of Anthropological Research. And I actually posted the website where we found sort of the best information most succinctly. And yeah, it's sort of a fun story. It records actually the breakup of this group, something about some pay structure within the karate club or something. So they originally, I think it was only a partitioning. How did this group partition amongst friends? It's been used and extended since then to actually talk about modularity, sort of deeper modularity. So if you look at this little structure here, the 4, 5, 6, 10, 16, these guys actually stand out. These nodes stand out. I don't know who 11 is. That's sort of a, so, you know, that's a single edge to a single person. It's like a, maybe they came in late to the club. The story would be interesting. But over here, this is the most interesting one. This is truly like a little cluster here. And if you partition it into two pieces, we'll see maybe this, you know, how this behaves. But eventually you'd expect if you had a certain modularity, you looked at for communities, this should maybe be its own community. That's sort of an intuition behind community detection. And there are a number of ways to do community detection. So if people are familiar with graph, with sort of network analysis, it has been, actually, I mean, community structure has been, you know, highly studied. But also the ways in which to do it are sort of varied as well. Modularity is, I put it here, but it's essentially looking at how does the structure of a community, if you choose a community, you know, sort of pick a community out of the graph, how does that edge structure differ from what the expected edge structure would be if you had a null model? Okay, so you want to essentially, the null model is essentially an equal probability of an edge between nodes or something like that. And for communities, you should have much higher connectivity between them than the null model would give you. So you want to maximize that with your communities. So what we're going to do here is go through a few communities. So we're going to have 2 communities, 3 or 4 communities represented by C. Possibly 4 choice of variables. Here's capital K and small k, my bad. But essentially, here's our karate club graph, and we're setting K, which is sort of a typical, I don't know, we chose this because it's sort of the typical argument for the communities. But so we set K equal to C. and you call the community detection algorithm, which does, a similar thing to partition. It takes K and the number of communities and forms a modularity matrix from those, and then maximizes that, or minimizes it if you put a minus in front of it. Then what we're going to do is sample, basically take the best solution we find, map it to an equivalent graph with node labels, and plot stuff, and compute the modularity too. So let's go through that. And so you can see it, we upload, and we get the modularity for each of the community, each community number. So pretty low, actually, relative modularity for 2 communities we see here. We broke up. I believe the 2 community split is between, basically it's Mr. High and John A, club president and the actual karate coach. And that was the original split. But there's actually higher modularity based on the friendships. And we see that here for 3 communities, we have much higher, more than doubled our modularity. And you can see them represented here. And this is that little cluster we saw originally. And then we've got 2 other communities. And then if we go to 4, this one always renders a little oddly. It's actually slightly higher modularity. You can see compared to 3 communities. And, but it's not as clear, at least in the way I've been able to draw it. So, but the key point is we can actually take a karate club graph and quickly loop over all of the possible communities. We could continue on from here, but the communities measure the modularity, and then you can plot them actually. And I should point out that the plotting does not come with Mukai. There's a utility module that I made the plotting. So let me dive in for 1 second. There's a subtlety here. Just if you are looking at this, you may have noticed the encoded samples. So because we have to, a lot of algorithms, if you're going to use binary encoding, because we're looking for binary solutions, we have to sort of give options for each of the nodes. And so we have to encode them as node 0 can be assigned to community 0, community 1, community 2, like that. So we have to, in measuring the modularity, we have to sort of use the encoded version because the modularity matrix is actually formulated with the larger number of choices per node. So, but that actually, if you're doing stuff with that, that actually does come with the, response object as well. So, and with that, we've sort of quickly, but hopefully effectively gone over the basics, of installing and running some simple problems on Mukai. So if anyone has any questions, I'm happy to answer them, or one of my colleagues can certainly answer them as well.
Yeah, so Jesse, maybe if you want to stop sharing, and I have just a couple slides to kind of
perfect
end here, and then are you seeing my slides?
No, I'm seeing email.
Oh, sorry. Earth to Steve. Now are you seeing my?
Yes.
Okay. Earth to Steve. So I guess I wanted to give this slide just to kind of clarify what we're talking about here. So we used several different terms. The first is the whole product we refer to as Mukai. Jesse used, when he imported a package, it was Choir, and that's our constraint optimization API. Underneath that is QCI QB and then on top of that is QCI Network X. So this is kind of how those pieces fit together, and a little bit about You know, if you're writing applications, here are the different things you could call. And then underneath those, here's how we call various accelerators, quantum and otherwise. So just to give a little bit of a picture about that. So to summarize, we started a free trial of the Mukai software execution platform on July 6th. So this is based on the Mukai 2.0 release. So it has in it the APIs that Jesse just walked us through for primarily the constraint optimization is the new one. So it's constraints and objective, a bunch of performance improvements that we put in, and the community detection function that Jesse walked us through as well. If you want to get into the trial, here's the email to do that. And kind of in the shameless commerce division. So our software for constraint optimization is quantum ready and delivers superior performance today running classically. So you can check us out at our webpage, or you can send us email to get more information. And with that, I have some pointers here that might be useful. I will leave this up, and then we can answer any questions you might have. So one from the chat here, from Tomas. How do you handle inequality constraints? Jesse, you want to take that one?
Yeah, we can handle them as a separate, I think the easiest way is actually is in the next release, is actually building that in as a separate. So we have a cost constraint, we have a inequality constraint, and an equality constraint, and then we can also build in an inequality constraint as a separate argument. And I might actually punt that over to Raouf if we want more details, actually. So.
Okay, let me, how do I get there? Okay, I'm going to stop sharing. If anybody needs this information, tell me and I'll come back to it. Because, I'm not actually seeing Raouf on at the moment. Jesse, I'm not seeing Raouf on, so whatever you might be able to share is probably what we'll get today.
No, that's fine. Yeah, no, the short answer is Slack variables, right? So I would, that's really the most straightforward answer, is we can add Slack variables to handle that. And so the reason I mentioned you can handle Slack variables, I think either, I think the easiest way operationally to handle them is actually to send that in separately, and then it's, as a separate argument, actually as a cost and then constraint, equality constraint, and then a separate inequality set of inequalities, and then we can deal with that on the back end to optimize that, because a lot of those can almost be, we can do some linear algebra to simplify that. But short answer is
Okay. So there was one from Sahil. I saw there was counts in the output from the sampler. What do the counts means? Anything related to probability?
Yeah, it's the most, it's number of times we've seen that that configuration in the sampling. So yeah, you can relate it to what is, you can relate it to what is the probability or likelihood of finding that answer. But it is not a probability machine or anything like that. I mean, I should say that it's not. We're not sampling. You can interpret it as a probability, but that's yeah. I don't want to say that we're sampling necessarily from we don't have like a probability. some people, I think with things like quantum annealing, people are saying you're sampling from an actual quantum distribution. And I don't want to claim that, but we are, yeah. You can definitely interpret them as probabilities.
Okay.
Yeah.
And there's one here from Ashish Mehta. Thank you very much for this very insightful presentation. My primary query was, where would your systems fit in with the PQC phase? And Ashish, maybe you want, so Jesse, you may know what PQC is. I don't.
QC
so Ashish, if you,
yeah, go on, sorry.
Ashish, if you could clarify that.
Yeah.
There. Ashish, I've unmuted you, so you should be able to just verbally clarify if that's simpler.
I did come up with post-quantum cryptography. Is that Google?
Oh,
but I'm gonna ask Ashish to clarify if they could.
that seems like a good bet. So I guess, so the short answer is I don't know. I don't know how it bears on post-quantum cryptography.
Yeah.
There's
not directly if we're talking about Shor's algorithm, I would say.
right.
That's much further in the future in terms of actual quantum hardware. Let's maybe leave it at that.
Yeah. Other questions? So you can raise your hand, or you can type something in the Q&A or the chat.
Steve, do you see the topology question?
Yes, I was just answering that one in the Q&A in text.
And the Q&A chat is saved or it's recorded, is that correct?
Yes.
I don't know. Oh,
it is.
Okay. So Jesse, maybe I'd prompt you. Are there questions you normally get that we haven't asked yet?
A lot of people, I mean, ask about, depending on where you're coming from, about size. And we dealt with, I think the maximum size I showed was a 34 node graph. And so yes, I should point out that that's not anywhere near even the order of magnitude that we can handle. For the trial version, we've somewhat limited it just primarily due to some issues with requests, actually, to about 10,000, maybe 12,000 node. You call it node graphs, or basically 12,000 variable problems. But we can handle much higher things, actually, in quote unquote real life. We can easily handle 50,000 variable problems and stuff. So I just want to point that out. And Steve actually put up a one of our papers, I think, that points out some of those performance
Right. So I'll
benchmarks.
So I shared my slide here again. So this is there are two papers that are on the archive now. One about constraint optimization performance for graph kernels, specifically graph partitioning. Another one for QUBO performance. And those don't directly bear on size. I mean, large size is not a first order effort there. But we, we've gone up to, I think the biggest I'm aware of is 90,000 variables and 800 constraints, something like that. So
Yeah.
you know, a lot bigger than what we showed here this morning.
Yeah.
So I think that at least one of my answers that I typed in the Q&A may not be visible to everybody. So maybe I'll just kind of repeat those questions and answers verbally here. So Kunal Das asked what topology the qubits are coupled in with. Is there any documentation about QCI quantum computing in which Mukai software works? So when we think of QUBO in the Mukai context, it's a, I don't know what the right word is, a full QUBO, a virtual QUBO, which is not specific to any piece of hardware. So it's not, it allows full connectivity. Any variable can be connected to any other variable. And so you can just think of it as a fully connected graph or a clique or whatever's most natural for you. The documentation here, yes, I will copy all of this and paste it in the chat. Okay, so that's pointers to some of that information I just mentioned. There's also a question about what about reverse annealing? Is it possible in Mukai? So reverse annealing is a processor-specific optimization, and so our Mukai APIs are targeted at people developing applications and using applications too. And so we would represent reverse annealing in a processor-specific lower layer that we haven't really talked about today. I guess knowing what I know today, I would expect that things like reverse annealing are detailed enough and expert enough that we would probably deal with those in a lower layer. And so we wouldn't really think to expose control of reverse annealing to Mukai users. That's my thought today. That opinion could change, but really we want to know how to. In the case of reverse annealing in D-Wave's quantum processors, we want to know how to take advantage of that for a variety of problems and bake that into Mukai so that lots of people get benefit from whatever capability there is there, rather than asking each app developer to deal with that themselves. Okay, are there any other questions? Oh, something I should mention is, actually, let me re-share my screen. So here is in the yellow there is the URL for where the Jupyter notebook of this session will be shortly after we're done here. There's also documentation is available online, and that's pretty extensive. And as Jesse mentioned, it has the information about installation information. So that's high value. Are there any other questions? Oh, and we'll also post on the QCI website the video of this session, so you can come back to or refer back to it later if you need to.
A couple other questions in the Q&A, Steve.
Oh, good. Can Mukai handle continuous variables or only binary ones? Explicitly, we only deal with binary variables. Obviously, you can collect a few binary variables and make a small scale integer. That's fairly straightforward. We've done some experiments with that. and up to a small range that works well. But today we only explicitly deal with binary variables. But if you have thoughts or needs, we'd love to hear about a use case that you have in mind where you need something further. And then from Sahil, in one paper from arXiv named QCI QBSolve delivers strong classical performance for quantum ready formulation, there was Hamming distance information. It would be great if anyone explained in short how they are useful in optimization problem and can be used anyhow by Mukai. So yeah, this is a good question. So the one dimension of performance that is valuable for probabilistic processors, which quantum computers are, is this notion of getting multiple answers, which is, can be kind of a mind bender for people from the classical HPC world where there's one answer that is considered right and any other answer is considered wrong. But in the optimization world where getting the exact optimal answer is often impractical, getting a variety of good answers is actually a valuable thing. And when you have a collection of good answers, ideally you want them to be as different as they can be. So, if you're thinking about a traveling salesperson, for instance, and if you're thinking about a route and you say, oh, I could take one route that's kind of, a route to all the US capitals. You might have one route that kind of takes you through the southern part of the US and then up the western coast and then back east across the upper part and then down across the eastern seaboard. So that might be one way to do it. But if you want diverse answers, what you care about is that they're different at the subject matter expert level, in the problem domain. And so being able to see that there are answers that would maybe one would take you around the way I describe, and maybe another would zigzag north and south as you go west. And if you thought, well, I know there's a good chance of, if you're in if you're really using this for travel and you're thinking, oh, well, there might be a snowstorm in Denver, or there might be a hurricane in Houston. You might want to do something to go to those, to be more robust about how you travel to those cities. And so having answers that are very different is valuable. And so the way we normally measure that is in Hamming distance. Now, in the particular problems that we did today, we did not come back and measure those solutions in terms of Hamming distance. I mean, you could see some of that in what Jesse was showing. You get, the answers are bit vectors, and you could compare the bit vectors visually. But we didn't actually go so far as to call out Hamming distances and try to decide which solutions we would use by Hamming distance. But yeah, go ahead, Jesse.
The graph partitioning problem was probably maximally different. You split the graph one way or the other, and those are probably basically different corners of the space, intuitively speaking, because you basically just flipped all the zeros and ones. So that's one example, I guess. There's one example of, where the Hamming distance would, you could record it and see a huge Hamming distance. Whereas I think if you did Hamming distance on the community detection graph for the top two answers for each numbers of communities, they'd be pretty similar. So I don't know. Sorry to interrupt. Yeah.
Yeah. Exactly. So are there any other questions? Okay, well, we thank you again for attending, and you have contact information if you want to follow up on questions. And we'll post the video of the session in the next few days on the website. So thank you again for attending, and we hope to talk with you soon. Bye.